All right, all everyone. My name is Lawrence. I'm one of the observatory coordinators here at the observatory, along with Concha, who's somewhere here. Thank you all so much for coming out to our Governor Open House. It looks as though we've looked out once again, and there's beautiful clear skies. Hopefully, saying that the district said. Before we get started, I'd like to acknowledge that we're gathered tonight on the traditional lands of the Anishinaabe Northwest peoples. And I'm especially grateful to be here on this land, especially for really clear nights like tonight. I'm so grateful for the extra grateful. Tonight we have a really great talk from Mark Richardson. It's our special Dark Matter Day talk. Mark is the Managing Director for Education and Public Outreach at the Archibald Macdonald Institute for Particle Physics Research, Particle Physics Research. Mark did his PhD at Arizona State University. His research is primarily about how galaxies form and evolve. But tonight he's going to tell us a bit about the mystery of dark matter, the greatest mystery in astrophysics.
Cool. All right. Can everybody hear me okay? Who has seen me talk? All right, I gave one of these talks, it was last summer, and there was something about it that most people are used to me talking about dark matter. And so last time I talked about everything but dark matter. And so I thought this was fitting for me to come and give the other side of the conversation. And we're kind of especially located here at Queens. I work at the Macdonald Institute, which is a special place that's doing a lot of work on dark matter, among other things. So who here in the room has heard a talk about dark matter? I'm seeing a mix of hands. And to some extent, dark matter is exciting. I'm going to spoil the end of this talk now. We still have not found it. So that's what you're hoping to hear today. Hey, at least it sets your expectations somewhat. So I feel like there's a lot of these kind of conversations, especially around this time of year, because Dark Matter Day is October 31st. We're coming in a little bit late. I was actually doing a Dark Matter Day event in Burnaby, in Vancouver, last week. And so we are bringing this to you a little bit late, but we are kind of embracing the mystery that is this dark matter that we are continuing to hunt. And so I don't know which way these buttons go. Perfect. So yes, tonight's Dark Matter Day, but I thought there's some unique fun that is a little bit inspired by I think it was last month's talk, which was Brendan's, but maybe that was a couple months ago. This year's gonna work. About bringing in like the basic physics behind the science we're trying to do. And so I'm kind of calling my talk Astroparticle Physics and Dark Matter. So we can actually talk about what it is that the Macdonald Institute, the astroparticle physics community here in Canada, is actually doing. And that is not nearly as scary as maybe it sounds. And so that I can motivate that all of you can understand at a basic level what it means to try to look for something like dark matter. And that also extends to other things that we might want to study beyond dark matter. Stuff that we maybe know a little bit better. And so to start off with, I want to make sure we are starting at the ground floor. Everybody here is very happy and understands like where we're starting. And so the way I do that to give everybody these, especially a lot of the kids, is to go to Lego. It's like my favorite thing to bring into any talk when I'm giving about physics and particle physics. And that's because Lego is really, really, really cool. Because I can build whatever I want with it, and somebody else can build whatever they want. If you're familiar with Lego, this is a Lego castle. It's a Michelin castle. Here are Lego people to scale. I think Lego people is a known unit of length. And so this is there's a real castle that looks like this. But if any of you have used Lego quite a bit, you know you just can't get any old piece that you want. It only comes in certain varieties and flavors. And it's a matter of putting them together, and some of them don't go together the same way that others do. So you have to have the right ones. But by putting them together the right way, you can make exotic, cool things like this castle. I heard last year they introduced the Barbie house set. I was always a spaceship kind of guy growing up. And then also, I have a big family. And so then my cousin would come in the house and wreck the thing I built. And what are you left with? You're left with those basic building blocks. And the cool thing about this is, okay, there's a variety of colors, but it reminds me that, that really cool thing that I built that is maybe completely different than what my brother would have built if he had put the pieces together. At its basic building blocks, they all start off the same. a big crate of things, shapes, sizes, and these little dots. I think there's a special name for them, and I don't actually know what it is. And so that's what you got, right? You get in, you have your crate of Lego, you look at it, and it's like, you only have what you have, they only come in so many ways. I know if anybody's gone to a Lego store recently, they have more and more exotic, unique, like fundamental shapes. But at its heart, you only have certain pieces. It's kind of the creativity of how they go together allows you to build such diverse things, whether it's a castle or the space shuttle or whatever. And so this is what I'm used to as a kid growing up, putting things together and building things up, and seeing the diversity of things I could build from a fairly non-diverse collection. And when I become a physicist, an astrophysicist, I start studying with the universe, and I find out that the same can be true for things. And this has kind of been known for a long time, that even everything around us, including the Lego blocks and the piece of paper and myself and the computer that I'm using, are also built out of fundamental building blocks. I can take a hammer and destroy my computer as much as I want in smaller and smaller pieces, and eventually maybe I get to the building blocks of a computer. And a lot of us are familiar with what that looks like here. This is an atom. So we have, this laser doesn't work, so I just need a big pointer stick. In the center is this nucleus of the atom, and then you have the electrons that go around it. And the atoms, the way they go together, tells you about like chemistry of this thing and the periodic tables, what we're used to. That's for chemists. If you want to be a chemist, go to Chernow, to Ellis or Stern. We want to get deeper. I still have my hammer, or a really, really powerful tool, like this guy over here. I smash these things together, I find that they're actually built with smaller pieces. And that's kind of the end of the story, in the sense that when I do that, I find that everything I've ever thought to smash together or smash apart can be broken down into just 17 different pieces. This is the poor man's Lego store, right? And that's the universe. I go and there's 17 buckets. I'm gonna get this piece, this piece, this piece, this piece. There's 17 of them. And somehow by putting them together in every which way, I can make me. I can make my computer. I can make everything in this room, everything in the universe. And so particle physics is the study of this stuff. What is the stuff that builds up everything? Because we don't know everything about it. And it's a really cool thing that scientists like to know, is just try to know everything we can, to understand the nature of these things. And so particle physics is trying to get to know each and every one of these characters, these blocks that you can get from the universe's Lego store. And so, I have all of this, and so what I'm really need a big, it's over here.
Oh, you don't want to.
How was that idea? There's nothing in each one there that wouldn't break the computer. But every one of these squares is supposed to represent a type of building.
Oh my goodness.
All right. So way up here, you have the up court. These collections are called the quarks. They build together the protons and the neutrons that build the center of atoms. We have the electron, the mu, and the tau. These are these other particles. The electron is very common. It makes the electricity that we're used to. And all of these guys have a range of masses from as low as 0 to something. All of them have different charges. They have different ways that they interact with each other. All these guys on the right actually explain all the forces, the ways that interactions can happen. And so particle physics is somehow doing science, doing experiments to answer, hey, tell me about you. Tell me what makes you tick. Tell me your strengths. And this isn't that different than maybe me diving into a bunch of MC or Marvel comic books and trying to get to know my superheroes and supervillains. They have different strengths. Some of them are really strong, some of them are weak, some of them are massive, some of them are not so massive, like poor little raccoon. And so, at the end of the day, scientists, particle physicists are just doing cool research to try to get to know these characters, the characters that make up the universe. And so to do that, I don't rip up my piece of paper many, many, many times to get to these building blocks. I have to use big pieces of technology to get to these answers. And so this is the Atlas detector. It's actually made in Vancouver, partially in Vancouver. It's located in Europe at the CERN detector, that Large Hadron Collider, the LHC, one of the biggest experiments in the world. And here is a human to scale, another characteristic unit of length. And so you can see this thing is massive. And this is what we need to use So we can smash these kind of, well, even bigger particles together, where when they smash with enough energy, they break apart and make all of these pieces, and when they fly through this detector, we're able to. And so my hope today is partially to convince you that that process isn't that hard. You know, we've since learned to hone and do it a bit better, and I'll talk a little bit about that. But I want to try to convince all of you that you are, to some extent, all particle physicists too. And so maybe to motivate this a little bit more, because a lot of times I get to the end of my talks and I hear why. Like, why does any of this matter? Is it just good to know this stuff? And absolutely, I agree. It is just good to know this stuff. And I want to motivate that. I think first and foremost, as a scientist, I think there's intrinsic value in us spending resources, spending our time, spending manpower to just learn about the nature and mysteries of the universe. Because I think all of us as people have that kind of fundamental interest. Like, why are we here? How did we get here? What is here? What is the nature of the universe? What's going to happen? Why did the Earth, form? Why are we on here? All these kind of questions. And they all relate down to fundamental principles of the universe. And so, yes, giant room, pointing to that, I think there is value in forming a deeper understanding of the nature of the universe. This is a lot heavier than it is. But there's other things too. Each and every one of you, to some extent, probably interact with ways that particle physics makes us a safer world. And I think it's important that you guys all appreciate that too. One of the most common examples of this is in medical analysis. If you know somebody that has, say, a brain cancer or a tumor, you might use a PET scan to detect the nature of that tumor, to understand if it's operable or not. And so that kind of medical analysis heavily relies on both understanding particle physics and being able to really, really well detect particles. In fact, we put in a radioactive dye into patients, and when it then goes to the tumor, because that's where the immune system is fighting, it makes high energy particles, and we need to detect where those come from. And that paints us a picture of where the tumor is. If we don't have the ability to understand how to make that radioactive dye, if we don't have the ability to test and measure those particles, then we can't do really, really important science or really important healthcare for patients. Another example is just radioactivity measurements. I'm just waiting for the day that I have the chance to go and hang out in Chernobyl, for example, where, is that a safe place that I want to go? And so sometimes we're in environments where it might not be safe. So being able to detect radioactive particles, these fundamental particles, some of those 17, is an important skill that we can have. So you can use things like a Geiger to be able to measure those, to understand what the safety is, whether it's in Chernobyl or in your basement. In fact, October just passed, which is a radon awareness month, because radon gas is the #1 cause of lung cancer if you don't smoke. And so that's a particle that could be in many of your basements, because Kingston is built on a bunch of limestone, which has uranium. So that's another example of where particle detection is. Another one that's very common is smoke detection. A lot of smoke detectors rely on the principles of particle detection. When smoke gets in, it actually disturbs the ability for this to detect a certain particle that's inside some smoke. And so if we don't have the ability to measure that, we can't make super sensitive smoke detectors that maybe aren't so important for the house. But there's actually new technology trying to make new smoke detectors that can trace really, really light wisps of smoke when you still have a forest fire. So this is just like an example of trying to convince you all that, hey, particle physics is first cool and important to go. So if I want to be able to detect it, I need to ask myself, what are the things I'm detecting? And I've already kind of given a spoiler alert for some of that when I went through those 7. So let's think about what a particle might be. What is the thing about a particle that I might want to reveal to me as a particle scientist? One is maybe just where the heck is it and how big is it? So its position and its size. And size is a weird word for particles. If something has physical size, then it's usually not that hard to imagine you can make it small. And so for the most part, we think of particles, fundamental particles, as actually having no size at all. They are point mass. They are infinitely small. So what do I mean now when I say size? Well, what I put here is these rocks. And so there it's really, really easy to think about what I mean by size. Well, it's like, what is its size? Well, what's actually telling you? What's the observation that's giving you that information? It's the fact that, well, when I'm this close to it, I see it, and when I'm further away, I do not see it. You know, it's basically how close do I have to get to it to interact with it. So at what point is the broom covering the sky? And the same can be true. Okay, broom is a cat. The same can be true for particles. Particles, like I said, some of them get along with some of them don't. They interact with each other. And so by size, we kind of say, how close do I need to get to it, or can I get to it before I start having some kind of interaction? And then the size then kind of depends on whatever the nature of that interaction is. I'm going to sweep that under the rug. The next thing is the mass. This is this word I've said a few times. I want to make sure we're all kind of with it. I don't know how heavy it is or how resistant to movement it is. This, you know, if you've ever gone to the gym and lifted weights, you're probably a little bit familiar with mass. Heavier things, more massive things are harder to lift. So I just have our proton and the neutron to think of before the atoms kind of here, just showing you kind of heaviness. And so maybe understanding how massive a particle is an important thing as well. And there's something that a particle can have, I can have two protons and they can actually be different in terms of energy or momentum. But these are ideas that we are familiar with here on Earth. You can give a young child lots of sugar, she has lots of energy, you get her moving, maybe she has a lot of momentum. And so particles too can have a lot of energy. You don't give it to them by sugar, you give it to them usually by pushing them really fast. That can get them moving quickly, having a lot of kinetic energy. But there's other ideas like, listen, what's louder? I don't know, that's kind of loud. Maybe they're almost the same size, but when it was higher, I gave it more potential energy, that allowed it to transfer to kinetic energy, and then it made more noise energy when it hit. And then momentum is kind of an idea too of how much that thing is moving. And it's a different property than energy, but maybe you think about it a little bit in the same way. But particles have these two different things, and they are related. And then this other idea is charge, and if I hadn't have Van der Graaf, I didn't feel like carrying that over today, then well actually no, I cut my hair recently, so that wouldn't work so well for me, but when we put maybe a kid or my colleagues on a Van der Graaf, I can give them a charge, and like charges repel, and so when I give everybody the same charge on their hair, all their hair will be. Well, the fundamental particles that build up the universe also have charges, and so we want to be able to detect those as well. And so these are like kind of the more common properties that we want to detect. And so here's the problem that I want, this is like my take home. I want to achieve something with all of you today, to make you all particle detectors, is how do I solve this problem? If that is my goal as a particle scientist, is to do experiments to actually detect particles, how am I going to do this? And what I want to convince you, for the most part, is fundamentally, at the easiest point, when you're like the very first particle physicist to do this work, this isn't that hard of a thing to do. So how can we detect these particles? Well, one is to rely on some of these properties and some of the ideas we have about the universe. For example, conservation of momentum. That is, that one thing moves, if it bumps into something else, then it's transferring some of that momentum. So if something suddenly moves, it didn't move out of nowhere, it moved because it got some kind of boost. So an example of this is here. You're looking for the light.
No,
The Roman camera. I don't know, it's probably almost the same size, but for those that can't see it, this is a cool device. It's called a ballistic pendulum. And it's a fun way for me, well, for physics students in our first year, to talk about things like conservation of momentum and energy. And so this is going to be my particle. And based on this gun setup thing, which is basically just a spring, I'm going to give it some momentum. And what I can imagine is, what if this is something I can't see? This is one of these invisible particles that I can't see, because, you guys can come to the McDonald Institute later tonight and actually see some of these real particles. But for the most part, there are particles up to us, the air that we breathe, and you can't see it. So what I want you to imagine is this is one of those particles. And when I hit the trigger, it's going to have some momentum, and it's going to move. And this is my detector. This is something I see. It's just kind of hanging there. And maybe there's a way that I can actually use the detector to detect how much energy that has. And so I've launched it, it hits my detector, suddenly my detector, remember, imagine I cannot see this particle. Suddenly my detector moves. And built into this detector is the ability to actually measure something. If it had more energy, this might have gone up higher. If it had lower energy, it might not have even reached this little stop. Okay? And so exactly how high it goes is related to how much energy it is. And so all I need is to build something that can be hit by something, and I can tune it just right to then measure some of these fundamental properties. And that's not that different than this. In fact, I could, with the ability to like change the spring of this, but I doubt I can pull this off on the fly like this without causing an issue. But I mean, I didn't see exactly how high it came, but if I changed the conditions of the initial momentum, I then get a different result. So that can be useful if I want to study different types of particles with different. So I don't think I changed this enough to make a difference, but hey, I get to do the experiment again. I think it went a little bit higher. Anyway, that's like a really, really basic principle of showing conservation of momentum, conservation of energy. Another example could be this. I have a bottle, we've already heard that it can make noise. Well, I can put it right on the edge, and so it's just kind of waiting there. And then if a particle comes along and hits it, this is why I'm not an experiment. Now, it falls, but I set it up in such a way that when a particle interacts with it, I hear something very different. I hear a noise. And so that's just the same thing. Those are two particle detectors. It's not, like I like to say, it's not all that complex. It's a matter of setting up your experiment so that you can learn something specific and quantitative when that detection finally happens. Any questions about that? I'm going to do this backwards. There's other examples of this with conservation of energy that's going to come up today, where maybe moving things hit something instead of making sound or making motion, it leads to heat. So that's a nice way that we can detect things too. And I'll show you an example of that later tonight. You know, this is the bare bones basic stuff. But now through technology and 100 years of perfecting on these methods, we now have computers that go a long way. So that when we use electronic tools, they can capture this information. So now we don't just use our eyes to detect light particles, maybe we use cameras, use the James Webb Space Telescope. You know, we're always kind of improving and maximizing the ability of these detectors to work. Right. Yeah, I'll save that one to later. And so here's an example, spoiler alert, for what you'll see in the Bell Institute, and maybe I will just dim the lights a little bit. What do you think? Is that okay? Yeah. So this is one of my favorite particle detectors, and it's just over in the Sterling Mall. Every time I do a demonstration with it, I see something surprising. So that's kind of cool. And so this is an example where you actually see individual particles because you set up this detector in just the right way that when a particle zips through, it basically makes a signature that you can see. And so when you come over tonight, I'll explain maybe in detail exactly how this works. But the cool thing is, you know, when you first built one of these cloud chambers, it was originally designed a little over 100 years ago. Awesome, Yuan from Outer Space. You originally set this up, you didn't exactly know what you were going to see. All you knew is that you're going to see something. So there was a bunch of stuff that you didn't know about. And then you put this on, and suddenly you start to learn what you don't know. You start learning the questions that you want to answer, and that then tells you the next system that you need. Something by looking at this, you might notice is there's kind of 3 different types of particles you see in here. And I've labeled them here on the right, alpha, beta, mu. This is not what we have in Sterling Hall, but you can take some of these and put in radioactive blocks, like I was talking about earlier, and there they're spitting out all of these alpha particles. And so this is the same stuff that Marie Curie might have seen 120 years ago when she first discovered radioactivity. There's other examples of seeing these kind of cool particle interactions. We got to see this just last month. Seeing some hands and kind of the sex, I'm not seeing everybody's hands. This has been a really active year for particle detection in the atmosphere. The atmosphere can also be a bit of a particle detector. And that's because of the northern lights. So we're at a solar peak, and we heard a little bit about that from Brandon a couple months ago. I really can't remember if it was last month or not. But we have these collection of really energetic particles that evaporate from the sun, eventually comes and they hit the Earth, and because of the Earth's magnetic fields, it gets directed towards the Earth. And then the different colors actually tell us different properties of the Earth's atmosphere that's being hit. And so you can actually learn a little bit about the energy, what's coming in. People okay with the light level? Can I keep it at this level? Seeing some nod. All right. So there, I've tried to bring you all up to speed to be particle physicists. To some extent, you understand that we're just trying to use tools like conservation of energy, conservations of momentum. If we have a way that particles are going to interact with something, and particles could be as simple as my finger, or it can be one of these fundamental 17 particles. When they interact with something, we can measure its properties based on how it changes our spectrum. And so then what is at the forefront of maybe particle physics and particle astrophysics, which is where a lot of what we use here on Earth isn't as good as what the universe itself can kind of tee up for us, for actually doing kind of big science. And so today there's two big mysteries at the forefront of physics and astroparticle physics. One of which is the nature of the neutrino. So I thought I would highlight that we are the arts of being developed in Astroparticle Physics Research Institute, named after Dr. Aaron McDonald, who won the Nobel Prize in 2015, for basically solving one mystery in physics relating to neutrinos, and along the way revealed two little things. Our current model at the time of those 17 particles of the universe says 3 of those particles that were at the bottom, if you were looking, called neutrinos, are completely massless. That is what that model says. They have to be massless, just like light. Art's work was basically proving a bunch of scientists wrong, in that the universe doesn't care what our model says. They do things. At least 2 of them. And so in the process, that means our model is wrong. And so it opened up a much bigger mystery, which is if they have mass, then what is wrong with our model, our mathematics, our understanding of those 17 particles that says that they have mass, even though we don't understand how they have mass. There are ideas of how they could, and there'll have to be little adjustments to that model of those 17 particles. But good job, Art, showing scientists wrong, because this is the new mystery to go and explore. So this is one of the big mysteries, is trying to understand how those particles have mass, and maybe it explains why there's more matter than antimatter in the universe, among other things. How am I doing? The other thing that's at the forefront of physics today is dark matter. Remember seen the show Dark Matter? It has absolutely nothing to do with dark matter at all. The one thing I will say is the protagonist is an astrophysicist, and so as an astrophysicist, it really, really frustrates me because I find that he is sometimes not that smart. And I just assume it's like the benefit to like make sure everything is like explained enough that the audience can follow. But anyways, I was frustrated. But no, not that dark matter, this other stuff dark matter. And so I wanted to take a couple slides. Oh, I should say, so the McDonald Institute is basically that community of astroparticle physicists that are trying to solve those two kind of mysteries among some other stuff. And so we are a broad community across Canada. This is not the kind of research you do in a single lab anymore. This relies on world-class facilities like Snow Lab. And so we are a partnership of almost 20 different institutes across Canada working together to do this, using facilities like Snow Lab in Sudbury and other places. So yeah, we're based here, but we have partnerships across all of Canada. So we're here for Dark Matter Day, Dark Matter Night, and I know most of us have probably had a pretty convincing explanation of why there's dark matter. But I think it's important for those that aren't in on this to reveal some of the story of how we know that there's this stuff, this mystery. I mean, it is one of the two fundamental forefront of astroparticle physics mysteries. And so a few of you, this might be old hat. If you want, maybe, yeah, I'll explain it. So rather than bringing you up and taking your turn. But I hope this is still a little bit. And so it goes back to this idea of science, and science is our effort to try to understand the universe. And so scientists are all the time looking around, seeing the system, seeing the things around us. And so one thing that some astronomers will do is look at all the planets, here, every single one of the 8 planets, and observe them. And like scientists do, they often find some quantitative data that they can measure about this system, and then see if there's any relationships between them. And so you could make a nice table of basically the distance of each planet from the sun and how fast they move as they travel around the sun. And so you could make a nice table like this. But humans aren't very table-friendly people. We like pictures. And so the way scientists usually do that is they make a nice graph of data and see if it tells us something. I can't look at this and see any kind of trends, any kind of information for me to understand. But when I do this, I can. And so what I've done is I put all 9, there's 9 planets now, and Pluto, each of their own. And so I plotted them on the x-axis and how far they are from the sun, and on the y-axis is how fast they're moving. And what I see now that I'm on a table on a nice little picture, I see that for whatever reason, as I go to the right, I get more. As I go to the left, I go. What does that mean in terms of this quantity? As I get further from the sun, I get slower. Planets don't have to move so fast for some reason. As I get closer to the sun, I have to move faster. And if you know anything about gravity, gravity likes to pull, and gravity's stronger when you're close to the pulling object. Well, the pulling object here is the sun. So if I'm Mercury super close to the sun, if I don't want to fall into the sun, I gotta stick around. Otherwise, I'm gonna fall in. But if I'm way out Pluto, I'm kind of away from the clutches of the gravity of the sun. And so if I move really fast, I just go, and then that would be fun for nobody, right? We want Pluto to stick around. You matter, Pluto, I swear. And so it gets to go slower and still hang around. And what I can do to like really convince an audience of people that I know what I'm talking about is I can connect the dots with a blue line, right? And then that proves that it's something. I want to highlight that that blue line is not me connecting the dots. That blue line is a prediction. It's me applying my understanding of gravity as it pertains to Mr. Noisy Bottle falling off the table, an apple falling off the tree, even the moon going around the earth. I apply that thing that scientists have already kind of come to understand about the universe, and I apply it to this new system I'm studying. But it has to hinge on one kind of important assumption. And that assumption is that most of the mass in the solar system, which explains most of the gravity in the solar system, is where most of the light is in the solar system. And basically 99.9 and a lot of 9% of all the light in the solar system comes from that bright thing on the left. But that doesn't look that bright here. It's called the sun. I think when I go out last night, and I'm hoping tonight's like it, Jupiter was almost blinding. So bright, but it's reflecting light. That's not even light coming from Jupiter. If I want to see light coming from Jupiter, I actually have to go to like deep infrared, where maybe its surface is even colder than human. So you think about infrared lights for seeing humans. That's where I'm going to be able to see a little bit of light coming from planets. And so my understanding of gravity, folding in this assumption that most of the gravity, most of the mass of the solar system, where most of the light is, gives me this line. That line is independent of all of these dots to some extent. I can change the mass of the sun. So I don't, it's hard to go out with my scale and weigh the sun. That is one number I can change and get that line to some of the good. So the fact that my model for explaining gravity matches all of my data means maybe not confirmed, but really strongly implied that my prediction that almost all of the matter in our solar system is where all the light is. Scientists always want to kind of go, okay, then what? And then what? We write a paper, we then say, what's the next question we're going to have? Well, when telescopes got better, we wanted to look at the next big thing in the universe. So what's beyond the stars and the planets? Well, it's the stars and the galaxies. So you can imagine that you go out and look at one of the nearest full galaxies. It's not a galaxy we're in, so it's a little bit easier to see it. This is the Andromeda galaxy, and I've just taken a cut, threw it up here, and then here you can kind of see the brightness. And you see it's not like the sun. All of the brightness isn't just here, but I think you would agree that the center is the brightest part of it. And then it's still bright, and then it kind of dies away, so it's not as simple. But kind of the way I see the light, and I'm going to assume, just like in the solar system, where the light is where the mass is, most of the mass is in the center, but there's still some out here, coming from all of the stars that make up the galaxy, the hundreds of billions of stars. Just most of them are the same. And I can apply then my understanding of gravity as I learned it about atoms. Learned about it with the moon, now I learned about it with Pluto and the other planets. I can now apply that and come up with a prediction that when I measure the stars that are orbiting galaxies, I'd expect something similar. Galaxies aren't ripping themselves apart. Galaxies are not falling in on the black hole at the center. At the center, some of those stars better be moving fast, so they're not falling in. And as I get further away, there's less mass, less gravity, so I should expect the stars to have to travel so fast. Otherwise, they fly off from the galaxy. And when I go and I do that observation, or I don't do it, Vera Rubin does it, she measures something much more like this. The big difference. So again, this is exactly what Vera Rubin did in the 70s. This is the expected line. Okay, so my safety glasses. So this is based on the light of this galaxy, the different galaxies, the triangular galaxy. This is how fast she expected the stars and the stuff in the galaxy to move as a function of distance. All the light isn't concentrated right at the center, so it actually takes a while before you feel much gravity. So you actually don't have to be traveling that fast right at the center. So you get a bit out, then there's no more stuff. So you should be able to travel slow. But when she did the observation, she found that stars just keep going faster and faster. And then she was even able to measure gas clouds, and they just kept going faster and faster. So you have two options. Galaxies are ripping themselves apart. Except when we go up and look at the universe, we don't see any galaxies doing that. It's moving way, way, way faster than the gravity says it should. And you expect this stuff to just fly away. But they're not doing that. The other option is there's extra gravity. Your prediction that mass traces light is wrong. And that's okay. It's okay to be wrong. We've already seen that. But it means that there's a mystery. What is this mystery? And just to, I should say this, like, science is actually only really exciting when we're wrong. Like, that's when we know, like, oh, we haven't figured everything out yet. I still get a job. More importantly, I haven't reason to get out of bed and do a new little experiment. That's when the universe tells us we're wrong and that there's more mystery there. And there's lots of examples of this. There's the Mercury does this weird thing where its orbit kind of, this is vastly exaggerated. But this was a hint early on that Newton didn't have the full answer, that general relativity had to come in to explain how the orbits of planets work. There's also this, where maybe the speed of light was, different for different people. So if I have a light moving in the same direction as the Earth is moving, I'd measure something different than if light is traveling at a right angle. And so Michelson and Morley developed an experiment to confirm that. And then they didn't get that experiment result. Instead, they see the same thing. So this idea is like, here are my experiments moving with the Earth in this direction. If light has the same speed, then these light come back at the same time. If they don't, then they take different time to get back. So they're able to see. Hell, there's even examples where, there are mysteries. And, we don't even think we're right. We don't think it's right, but, we still produce it and publish it. Like this example, I forget even the year, it was like 15 years ago or 12 years ago. They were seeing faster than light particles at CERN. They didn't think they would be real, but they shared their information so that somebody else would help them solve this mystery. And so sometimes, your experiment's wrong. And so being wrong isn't the end of it. And so no matter where we look in the universe, whether it's inside the stars moving around galaxies, we look at galaxy clusters all moving around each other. We can look at some of the very first pictures from James Webb Space Telescope, and we see these weird shapes of galaxies. They don't all look circular. Some of them look like arcs. We can even find some that also look like full circles. This actually shows us a way of weighing the amount of mass there, because these weird shapes are caused by the gravity bending the light. And so stronger gravity means more bending. And we can see how much visible matter is there from the light. And now this tells us how much gravity is there from how much is bending. So we can use this to measure the universe. We even have examples of bullet cluster, yes. Where we actually take clusters of galaxies like these guys here. Sometimes they happen to go through each other. Galaxy clusters are mostly empty stuff that's permanent galaxies, so they just kind of go through each other. But there's stuff between galaxies called gas. And when those clusters come together, they hit and they collide, and they make a lot of bright X-rays, which you see in the pink. But you can do the same kind of weighing exercise you do here, and looking at all these background galaxies and figure out where all the gravity is distorting the shape of these galaxies. And that tells us all the matter is around the blue. So this is called the bullet cluster, and it shows us that all the matter, almost all of the gravity that we see in the system is not where we see anything. And so this is a collection of all independent, strong indicators that there's this extra stuff in the universe, this extra matter. And so we collectively call that extra gravity, that ignorance on where that extra gravity comes from, dark matter. And so this is this big mystery. We actually can go out and weigh how much of it there is in the universe. I told you, everything we ever interact with at a lab is these 17 particles. But when we go and we weigh the whole universe, it only makes up 15% of all the matter in the universe. When we do this other exercise of finding this dark matter, we actually see it makes up 85% of all the matter in the universe. So we don't know what it is. But one really good idea is that just because everything, just like everything else, is a particle, maybe it's a particle too, and we just haven't discovered yet. These neutrinos, again, at the very bottom, these bottom green lines, like these three ones, they were predicted 26 years before they existed. So it's not easy to detect every type of particle. When they were composed, it wasn't clear that we'd ever be able to detect them either. And so it's not unreasonable to think there's more to this picture, we just haven't seen that. But if so, it's revealing itself to us through the rest of it. And so maybe it has a place on the spot. I can guarantee you it does not belong at that spot. But for the sake of where there's space, that's good. And so you can come up with some kind of way to test that. And so that's the big question. How would you test this? And so I know I'm getting near the end of my talk, but I wanted to just give a very quick overview, again, of wanting to detect these things. We've already kind of gone through the path of making you all a little bit comfortable with detecting particles, but now we want to make special particles that can. So I want to tell you about 4 experiments that are doing this, and you can learn more about them when you come over to the McDonald Institute today. One of which is NewsG, and that's using this cool trick of ionization. And so this is a scale 3D model. This is the person to scale. And so this is this detector. It uses light gases to see when dark matter comes down. And so this is it when it was being built at Snow Lab, 2 kilometers underground. This is the sphere there. And this is, oh, I didn't put the picture in, but anyways, it is now complete and it's taking data. And when it does this experiment, you can actually see, this is what it expects to see for some particles. These are like a muon coming through this detector. So when the particle zips through, it ionizes the gas that's inside the sphere, and then we have a way of detecting those electrons that are free and interactive. And so we get these really, really, it's not a very strong signal in this plot, but this is supposed to represent a signal of what that looks like. This is what a dark matter particle looks like. It comes in, it only frees up particles, these electrons at one spot. And they slowly accelerate to the center of this object because there's a electric field in it. And when it hits, it ends up getting a bit of a different signal. And so this is particularly good at finding dark matter if it's a low mass particle. This is the big thing about dark matter. So it's one thing to know that there's extra gravity in the universe. We don't actually know its properties. We're starting from the ground up, like we're from ground zero. We don't know its mass. We don't know its charge. We don't know all these things, although we have reasons to think that it's within some kind of balance. The next up was a different detector using scintillation. I actually have a scintillator here. This is a type of material. What's up with this light? Maybe it actually has to heat up. I'll just keep clicking this one at a time. There are some materials that when a particle hits them, they actually light up. And, oh, there, now you look at it. So this is just a black light. Probably all seen these at a dance floor before or something. And so when you have a scintillator, it does something special. That when you hit it with energetic particles, including energetic light, sometimes they glow. So it's not quite the same as like fluorescence like you see in, I don't know, like glow in the dark stuff. This is actually responding to the particles that are hitting it. And so I don't know if you can see that kind of lighting up. But you can imagine where I'm in a room now without UV light shining on it. And then suddenly it flashes just for a second. That would tell me that a particle, a high energy particle, just comes through. And so there are detectors that we can build based on that principle. And the example of that is the Deep 3600 experiment that's running in the lab. And so it has a giant vat of liquid that's sitting there with all these special cameras, and it's sensitive to a different type of dark matter, a different mass of dark matter. Again, we don't know what dark matter is, so we have to kind of look for it everywhere. Oh yeah, do I have my audio set up? Things you always kind of forget. Preston, famous last words. And I probably need to share my audio for those online. Oh, this was a cool video. So this is a completely different idea. So not ionization, not scintillation. This is the idea of nucleation. So this brings in the pico experiment. Yay. Somewhere is probably asking me to okay to play a YouTube video. Let's see. Let's just exit out for a second. Probably. Okay, I can explain what she's saying, but it's a cool video, so I'll see if I can get it up. Maybe we're doing Q&A. But if you've ever taken a mug of water and put it in the microwave for too long, sometimes it doesn't boil. It becomes hotter than 100 degrees Celsius. So it wants to boil, but it needs a little push of energy. It needs usually a place for those bubbles to start. And so these kind of detectors are kind of sitting there poised to boil, but they need a little nudge along the way. And that can be maybe dark matter coming in. And so we can see that. We can see that here. This is actually the pico experiment. This is a giant vat of liquid that's very, very hot, and when the particle comes in, it makes a bubble. And the cool thing is, different particles make different bubbles and they make different sounds. So this one takes both microphones for listening to the detector and cameras for seeing the detector. So we can understand, this particle makes one bubble, but this particle makes a whole bunch of bubbles all over. The different particles have different things. The same way, remember back in the cloud chamber, we saw different kind of bubbles being, or little shapes being formed inside that. Last but not least, that I mentioned, the last kind of cool one. Yes, I'll say that. Is using actually heating, this idea of energy turns into heat. And here we can use one of these like super, super cool places in the universe. It's really cool, I tell you. But it's also really cold. And that's the idea if you make something very, very cold, at almost absolute zero, 0.015 Kelvin, and it's sitting there, and if a particle comes and hits it, heats it up a little bit, but it's made of a very special material that when it heats up just a little bit, it gets a huge signal, it kind of erupts and tells us that, hey, I just saw a particle. This is one of the most sensitive temperature measurements in the world. And so it's actually, to get it so cold, it has to be in this huge box within box within box within box, so that you can get, each layer gets a little bit warmer and warmer, so that outside you're at room temperature. And this is located at the snow facility. And so here you can actually see it being installed, is being built right now as we speak. It's really, really, really sensitive to anything. And so it's on these like stabilizers so that there's an earthquake. This is snow lab, it's in an active mine, then it needs to not basically be triggered by these things. And so these are four of a whole bunch of different experiments that all looking for dark matter in kind of different ways. And I will say, we do a lot of this work in a place called Snow Lab, because what we're looking for is all this other stuff. Remember the cloud chamber, we saw all those particles. Well, there's all these other types of particles. So 17 particles in the standard model. What we're looking for with dark matter is like listening for a pinpoint. And so where would you like to do it? You can also do it at a rock concert, or you can do it in one of the quietest places in the universe, which is this acoustically dead room. And so we use special facilities, and I mentioned this a few times. Snow Lab is one of the best places in the world to do this kind of stuff. It's 2 kilometers underground. It allows us to actually do these kind of experiments and block out most of the backgrounds and understand the rest. And so that's where we're doing this work. I was going to show you a video so that I'm out of time. So I'll just end with my last thought. Because I find when I do these kind of talks, and I hear these kind of talks about dark matter, doing all this work to go particle detector, to detect something we don't even know what it is, a lot of people sometimes feel a little bit dissatisfied. So what is dark matter after all of this, Mark talking or all these researchers working? And the answer is we still don't know. I told you this at the beginning. We still haven't found it. We still haven't seen it. If we have, I wouldn't probably be positive. No, with no price. Or not me, but all my colleagues. But I want to emphasize that even just trying to look for it, is saying, what if dark matter is this, and I wanted to try to detect it, just trying has enough. It's a bunch of people learning new science, learning new technology, learning new engineering to solve a problem, putting hard work, sweat and tears into it to basically build some new detector. Along the way, they're building that newer technology, and that technology can have better understanding of the nature of the universe, better understanding of the other stuff that's around us. And that can have implications for all the other places that particle physics comes into this.